vertical jumps at each element in 1, 2, and so on up to m. So when f bar of x is the halfway point in each vertical jump. And we see that here. Every time I have an integer, I have some probability associated with it, so f of x will jump. And f bar of x contains the bottom of the jump, which is equal to the last the CDF at the last integer, plus half of the magnitude of the jump. The magnitude of the jump is always p of x. So what we get is always halfway up each of these jumps.
Can I ask?
Yes.
Why would you need such a function?
Well, we're coming to that. So, actually, for the following reason. So, because p of x is positive, there's a one-to-one correspondence between x and f bar of x. So one thing we could do, we could create a source code by, instead of transmitting the binary letter x, we transmit the value of f bar of x. So obviously that's the basic idea here. There's a problem because f bar of x is a real number and does not necessarily have a finite representation in binary. So the idea is what we're actually going to send, the Shannon-Fano-Elias code word, is a quantization of f bar of x. So in other words, for each source letter, we get f bar of x, its binary representation. What we do is we truncate it, we truncate its binary representation and use that as our code word. So what do I mean by this? There's a one-to-one correspondence between x and f bar. Basically what that means is if I know f bar, I can map it back to x. And we can see that from my earlier example. So let me redraw that earlier example here. So f bar of x, the first element was 0.25, the next element was 0.65, and the final element was 0.9. So for instance, if I had a source code in which I replaced 1, 2, and 3 with those numbers, clearly I would be, if at the receiver, having received one of these numbers, I could immediately tell what element was sent. For instance, if I observed 0.25, then I would know that 1 was the source letter. If I observed 0.65, I would know that 2 was the letter. And if I observed 0.9, then I would know that 3 is the letter. So it's a one-to-one correspondence because because it's a function. In other words, each source letter has an f-bar, and it's invertible. The values of f-bar can be mapped back uniquely to x. They can be mapped back uniquely because this is an increasing function. And it's an increasing function because probability is increasing. Because the cumulative distribution function is increasing. In other words, because probability is positive. Yes?
You couldn't do that in the accumulative function because it's accumulative, the information is lost. Here you have two parameters. One, what's the integral of what's accumulated until then.
Yes.
And you have the instant probability's half value.
Yes.
So that makes it unique, I guess. Uniquely mappable.
Right. So yeah, you could arguably do the same thing with the CDF. It would still be unique, but what we're going to use some tricks that are specific to f-bar. So in fact, the specific trick that we use with f-bar is that we show, we quantize f-bar in a certain way, and we show that because we've quantized it in a certain way, what we end up with, we can guarantee by starting with f-bar that we have a prefix code, and we'll see that a little later. Whereas we could not necessarily guarantee that if we started with f. Okay, what we're going to do is we're going to take f-bar and truncate it. So truncate for each x. Truncate the binary representation of f-bar of x at L of x bits. So we'll just say for each of these source letters, let's get the binary representation up to L of x bits. So as a notation for that, let's modify the floor notation. So f-bar of x floor, that's the smallest integer less than f-bar, but what I'm going to do is I'm going to modify this notation with L of x, like so, and that is the first L of x bits in the binary representation of f-bar of x after the decimal point. So as a quick aside, how do we represent fractions in binary?
Choose complement.
That's how we represent negative numbers. So how do we represent fractions? Okay. Fractions in binary. Just as a quick aside, let's have, for example, well, okay, how do we represent decimal numbers in binary? It's, for instance, if I had the number 7, I know that this is equal to 1 plus 2 plus 4, which is 1 times 2 to the 0, plus 1 times 2 to the 1, plus 1 times 2 squared. So the binary representation of that is 1, 1, 1. On the other hand, if I have a fraction, let's say 0.5,